If you look at the road infrastructure in our country, we actually find that the majority of our roads in India are constructed as flexible pavements. And if we see the total road network, we actually find that majority of our road network, more than 90% of our road network, is coming under low volume roads. And a point what we need to remember about low volume roads when compared to the high volume roads is that these roads generally that does not create any revenue, unlike the high volume roads which we actually get revenue in the form of toll. The low volume roads generally does not generate revenue. As a result, once you construct these payments, the amount of maintenance funds that these payments receive will be very less. So it is very important to think when we go for a choice of a particular type of payment in the case of a low volume roads. We are actually believing that our low volume roads will sustain through its design life. So, but in many cases, such as when we actually go for flexible payments, typically with bituminous surfacing, we find that our flexible payments failing prematurely because of several reasons. Now, let us actually see what are the typical cross section of flexible payments what we follow in India. Now, as you all understand, flexible payments are basically designed as per IRC SP 72, and the Indian Road Congress guideline IRC SP 72. It actually provides two kind of catalogs. Basically, bituminous surface provided a bituminous surface placed above granular subbase and base layers. This is the first combination, and the second combination what they provide us, it actually allows you to have a combination where the bituminous layer is placed above cementitious subbase and base layers with a crack relief layer in between. Now, these are the two combinations of flexible payments that many of you would have implemented in your career. But we all understand because of several unforeseen reasons, our flexible payments fails prematurely. Now, this can be problems with respect to construction. Problems with respect to construction being if you're unable to compact the different layers to the adequate density, then our payments may fail prematurely because of this construction deficiency. So there are different reasons for why a flexible payment will fail. Now, three of the very common distresses what is actually found in our low volume roads flexible payment I have listed here. You can actually see the first one what I listed is edge break. As you all know, edge break typically occurs when our shoulder is eroded away and loading comes near to the edge of the pavement. So there it does not have any support, and as a result, you find edge breaks. Now, as the bituminous layers crack near the edge, the lower unbound layers, the fines in the material will also get eroded. As a result, you will find a big pothole forming in no time. Now, the second most common distress, what is actually found in the case of low volume roads, is basically rutting. Now, as you all understand, rutting is otherwise defined as permanent deformation or plastic deformation. You find these as longitudinal depressions along the wheel path, and you may actually find these kinds of distress in cases where your layers are poorly compacted, and in cases where you have uh, traffic loadings. You have excessive traffic loadings. Now, it can also happen that suppose if the traffic in that particular road grows exorbitantly larger because of any reason, say because of some unforeseen unforeseen sand mining activity or any other quarrying activity which is actually taking place, you find a large volume of heavy vehicles utilizing the road. As a result, you may find these permanent deformation or longitudinal depressions in the wheel path. Now the third very common kind of distress is what we find in the case of a flexible pavement is basically ravening of a bituminous layers. This is basically when you actually find your bituminous layers does not have sufficient adhesion between particle to particle. The coated particles does not have sufficient adhesion, and as a result, this is actually picked up by moving wheels. Now, one more important aspect of any payment is that any payment once you construct, it will start deteriorating with respect to time. But when you have deterioration, it is very important that you have to do a routine maintenance also. So if you don't do routine maintenance, your payments will continue to deteriorate to very low, to very bad levels. So in the case of low volume roads, we have all these unforeseen things. Okay, so lack of maintenance funds, inappropriate construction practices will actually result in premature failure of our bituminous surface, and this creates discomfort to the passengers. Now, these are some of the very common distresses what we find in the case of our low volume flexible payments. So the reasons I have listed here: unforeseen increase in traffic loading, poor maintenances, improper drainage condition aggravate the rate of deterioration of flexible payments. And in this context, let us actually look for why can't we move to concrete payments? Okay, why can't we move to concrete payments? Now, these concrete payments are typically provided in places where we encounter poor subgrade strength. So, as you all understand, in the case of a concrete slab, the slab is actually resting above a foundation. So, the majority of the load-induced stresses are dissipated by the slab itself. So, the lower layers have got very less role in the case of a concrete payments. So, concrete payments are actually preferred in places where we encounter poor subgrades. Now, where we encounter drainage issues, say even in your low volume roads, even in the roads which are constructed by PMGSY, especially when you encounter village areas or places where you have habitations, we tend to provide concrete roads, citing the reason that there is poor cross drainage facilities that is available there, or you don't have sufficient width to provide a cross drainage facility. So we cite these drainage issues and we tend to provide concrete pavement only in that specific stretch. Now we also tend to provide concrete pavements where your aggregate howl distances are larger. Now this point I have put up. Say if you look at your conventional flexible pavement, if you remember this particular sketch, it actually requires aggregates. It requires a subbase layer, granular subbase layers. It requires granular base layers. It requires bituminous layer. So in all these layers, when compared to your conventional concrete pavement, this actually requires larger aggregate consumption. So there are several places in India where you actually have a shortage of good quality aggregates. So in places where aggregate howl distances are larger and are costly, there also we can actually go for concrete pavements. And you also tend to provide concrete pavements in places which is subjected to severe rainfall. Okay. Now, one of the major advantage of concrete pavement is that even if the slab breaks, even if the slab undergoes cracking, unless the portion starts falling off, you will not find, or the drivers will not find, discomfort while you travel in the concrete pavement. Whereas in the case of flexible pavements, once a crack initiates, the bituminous surface disintegrates into smaller aggregate chips, and it will actually result much discomfort for the passengers. So this problem we don't have in the case of concrete slab. But what actually prevents many engineers from choosing these concrete pavements is that the relatively higher initial cost of construction. Now, if you look at our flexible payments, our flexible payments have lower initial cost of construction. And another reason why people actually go for flexible payments is that, especially in the case of high volume roads, they actually allow stage construction. So because of this feature, people prefer flexible payments over concrete payments, citing there are mainly two reasons. The first reason being high initial cost of concrete payments in comparison with flexible. The second reason is, in the case of flexible payments, I can go for stage construction, which I cannot do in the case of a concrete payment. Now, what we need to realize is that uh, when you look at the life cycle costs of these two payments, if you see the life cycle cost of these two payments, a flexible payment will actually receive a surfacing at the end of 5th year. It may require a rehabilitation at the end of, say, 10th year. So when we do a life cycle analysis, even in PMGS, right, when people do a life cycle cost analysis, we tend to allocate money for our resurfacing at the end of 5th year, and we tend to allocate budget for rehabilitation at the end of 10th year. So basically, if you take a 20-year life cycle cost analysis period, your life cycle costs, which is actually inclusive of your initial costs, which is inclusive of your maintenances and your residual value, you will actually find your concrete payments are much economical when compared to your flexible payments. But people, most of the time, they're actually worried about initial cost of construction. Let us typically brush up our idea about concrete payments. Now, in the case of concrete payments, you typically see panel concrete payments. Okay, you find panels of dimension of 3.5 into 4.5. It can vary in the case of low volume roads. Now, you find transverse joints. You find longitudinal joints also. So you may find the concrete slab resting above a compacted subgrade in some scenarios, or in some scenarios you will also find the slab which is placed above a unbound subbase layer or a bound subbase layer. So as I told, we have actually panels, or you can actually find grooves, transverse grooves, which are made here, and as well as longitudinal grooves also made here. We need to understand how does load transfer occurs from one slab to another slab. So basically, there are two mechanisms here for load transfer across the transverse joints. We have what is referred as double bars. So in transverse joints, we find double bars, and along the longitudinal joint, we find tie bar. Now, the role of tie bar is not exactly for load transfer. It is basically to hold both the slabs together. So this is the basic elements of a concrete pavement. So this we would have actually studied in our undergraduate classes. Now, but typically when you construct these pavements, the pavements are constructed as a monolithic unit, as a single unit. But we tend to form grooves within 8 to 10 hours after construction. And these grooves, once you construct, these grooves, once you cut, with respect to time, as vehicles starts moving, this is actually a zone of discontinuity. So there will be stress concentration here, and as a result, you will find cracks getting propagated to the down portion. You can actually see it here. Okay, so then this will actually function as one panel to another panel. Now we need to understand how does load transfer occurs from one panel to another panel. Now, in the case of a conventional concrete pavement, Say suppose if I'm talking about a low volume road, you may not find or you will not find double bars across these transverse joints. So basically, when a load is coming on this particular panel, the load is shared to the next panel by means of this aggregate interlocking. So you find an irregular surface here. This irregular surface will actually result in what is referred as aggregate interlocking. So the load that is coming to this panel is shared by the next panel by means of aggregate interlocking. Whereas in the case of a high volume concrete pavement, not only we have aggregate interlocking, we be having double bars which would be placed between these two slabs. So it is important that the load applied on one slab is shared to the adjacent slab for better performance of pavement. Now, granular interlocking is expected to occur along the crack. That means these granular interlocking will be mobilized over a period. Now, for low volume roads, adequate load transfer is basically expected by interlocking, and for high volume roads, this load transfer we are expecting by means of double bars and as well as through aggregate interlocking. Now, let us have a discussion now with respect to our low volume roads. Now, for low volume roads, the Indian Road Congress guideline is IRC SP 62. Now, for a conventional concrete pavement, our slab thickness, basically the design of concrete pavement, you tend to find out the thicknesses of the slab and as well as of the lower layers for a selected traffic and subgrade condition. So your slab thickness is basically governed by your traffic load repetitions, modulus of subgrade reaction, flexural strength of the concrete, the grade of concrete, whatever you're adopting, the wheel load stresses, and as well as the temperature stresses. Okay. Now, in the case of rural roads, say unlike our high volume roads, in the case of high volume roads, we may consider panel size of 3 into 4 or say 3.5 into 4.5 meters. Whereas when we come to rural roads, we consider typical slab dimensions can be of 3 into 3.75 meters, or this can be ranging between 3 to 3.75 into 2.5 to 4 meters, because our lane width is only 3.75 meters. These are single lanes. Now, the minimum slab thickness, what is recommended by IRC SP 62 is 150 mm. Now, this is one of the major item whenever we are preparing our estimates. We'll actually find providing 150 mm thick concrete slab throughout the entire length of the pavement would be actually resulting you a significant amount of cost for your pavement structures. So this is what people gets worried with. Now let us have a brief understanding about what are the different type of stresses in a concrete pavement. We are concerned about stresses which are induced by the wheel load. So if you remember, we are concerned about three locations. When the load comes in the center, when the load comes along the edge, and when the load is at the corner. So we are concerned about flexural stresses arising because of this loading condition. And we are also concerned about the stresses because of daily variation in temperature. Now, because of daily variation in temperature, I can have stress reversals, say from day to night. During daytime, your top portion of the slab is at a higher temperature with respect to the bottom portion. So the slab will actually have a tendency to curl up, but the self weight of the slab will actually prevent it from curling up. So it will pull the slab down. So when it pulls the slab down, this will actually tend to take a shape like this. It will actually tend to take a shape like this. So you have tensile stresses coming at the bottom. Okay, this is one thing. Now the second thing is at night times. Basically at night times, your bottom portion of the slab is at a higher temperature when compared to the top portion. So the slab wants to take the slab wants to take a shape like this. Self-weight prevents it. As a result, this would be the effective nature of the way in which stresses are going to build up. So you'll have tension coming on the top. So if we combined our wheel load induced stresses, and the stresses due to the daily variation in temperature, we can actually find the critical stress combination would be when during daytime, when the load is placed near the when the load is placed at the edge, and during daytime condition where I get flexural stresses at the bottom of the slab. These two basically your wheel load induced stresses and your temperature stresses becomes additive. Now another stresses what people tend to consider is basically your frictional stresses. This occurs when there is seasonal variation in temperature. Now this can be eliminated by providing a plastic sheet between the slab and the foundation. Now, when coming to low volume roads, basically if you see IRC SP 62, you find there are three cases which are defined. Case 1, when traffic is less than 50 cbpd. In that case, we design the slab by considering only wheel load induced stresses. The case 2 is when traffic is in between 50 to 150 cbpd, that is wheel load and temperature stresses are considered. Case 3, when the traffic is greater than 150 cbpd and less than 450 cbpd, where we tend to analyze wheel load stresses, temperature stresses, and we also tend to do what is referred as fatigue analysis. Okay, so the idea behind these three conditions is, say for example, when I'm considering case 1, there is a less likely chance that I would actually get the critical combination of temperature induced stresses and wheel load induced stresses at the same time. That is why in case 1, I only design the slab by considering only my wheel load stresses. Whereas when my traffic volumes increases, when it is between 50 to 150 cbpd, we tend to analyze the wheel load stresses and temperature stresses together. Both are considered. In case 3, apart from wheel load and temperature induced stresses, we also tend to do a fatigue analysis. Now the essence of any concrete pavement design is that you tend to calculate the flexural stresses arising because of wheel load stresses, temperature stresses, the combined stress, whatever the combined stress combination or the critical stress combination, the critical flexural stresses, whatever you compute, should not exceed the flexural strength of concrete, whatever you are considering. This is the essence of your concrete pavement design. Now, the major thing what worries our engineers is that our minimum thickness, what is recommended by the code, is 150 mm. So even when you're designing, even when you're designing pavement sections where your traffic volumes are very low, say for example in rural areas, when we have to provide a concrete pavement, especially when cases where we have poor drainage, as per IRC SP 62, you have to provide a minimum thickness of 150 mm. So there would be a significant difference in cost when compared to the flexible pavement alternative. So the question is, how can we still construct concrete pavements? Are there any other options? Rather than providing 150 mm, are there any other options? Okay. Now, yes, there are options. It is in this context we would be discussing about what is referred as short panel concrete pavements, self-fill concrete pavements, and interlocking concrete pavements. So let us understand the benefit of reducing the panel dimension. So basically, when we tend to reduce the panel dimension, the flexural stresses which are arising from the flexural stresses which are basically arising based on the reaction offered by the foundation would be reduced. So when you tend to reduce your slab dimension, your concrete layer will be predominantly in compression, or if you look at your bottom fibers, the magnitude of your flexural stresses is reduced significantly. So when slab dimensions becomes much smaller, say for example, in the case of block pavements, your interlocking block pavements, your slab dimensions are very small. That is also a concrete pavement. But when it comes to that, your slab dimensions are very small. As a result, you don't get flexural stresses. Okay, if you actually see your interlocking block pavements, you will not be finding cracks in interlocking block pavements, but you will actually find differential settlement in this, because each of those are actually experiencing compressive nature of stresses. So hence an effective way of reducing the load-induced flexural stresses is by reducing the slab dimension. Now, one additional benefit what we get when we tend to reduce our slab dimensions is that our temperature stresses are also reduced. Our curling stresses are also reduced. Okay, so these are the benefits. Temperature stresses are reduced. This consequently, our slab thicknesses can also be reduced. Okay, now I have highlighted this point before. Self-fill concrete pavements, interlocking block pavements, panel concrete pavements are essentially pavements with small slab size. Now the mode of load transfer or the load transfer distribution, basically from one slab to another, the distribution and the distribution of temperature gradient within the slab may vary with the size and the thicknesses of the slab that we are considering. Now, in this context, we all would have actually at least listened to, possibly if you have not constructed this, we all would have heard about what is referred as white topping. Okay, now at least we would have actually come across in newspapers that several city roads, such as in Bangalore and Hyderabad, are overlaid with concrete surfacing, and they refer to this as white topping. You actually have a concrete overlay over a distressed bituminous pavement. Okay, so this is what is referred as white topping. And if you look at the white topping photographs, you will actually see that the concrete slab dimensions, you will find it as a concrete pavement, but the concrete slab dimensions would be of the order of 1 meter, 1.5 meters. You may find square shaped slabs of this particular dimension. So basically, all these are panel concrete pavements. These are examples of panel concrete pavements. Okay. Now we have an exclusive Indian Road Congress guideline, IRC SP 76 2015, for the design of conventional and thin white toppings. Now, basically, these thinner concrete slabs, when we're actually going for thinner concrete slabs, we are trying to provide an alternative to thicker slabs at the cost of providing more number of joints. Basically, we are reducing the flexural stresses by providing more number of joints. We are reducing the slab dimensions. Now, IRC SP 76 2015 provides three types of white: conventional white topping, thin white topping, and ultra thin white topping. Out of this, we will actually find conventional white topping and thin white toppings being adopted in India. Now, say this kind of white topping can be adopted. This kind of white topping can be adopted when our bituminous surface is not significantly damaged. Say suppose if it is damaged, we will have to mill our bituminous layer, and we have to ensure that even after milling, we have a minimum of 75 mm of BT. But this directly, this white topping concept cannot be directly used for low volume roads. We'll be discussing about what is referred as short panel concrete payments soon, but I thought it would be relevant to discuss about panel concrete payments initially. Now, when panel concrete payments are implemented in high volume road counterparts, they basically mill the distress bituminous pavement and they would be placing the concrete slab and they would be cutting grooves after 8 to within 8 to 10 hours after construction. So the concrete, whatever they are using, it can be plain concrete or it can be fiber reinforced concrete. And the joints are made by means of saw cutting or by means of placing plastic strips. Now the analysis of white topping is similar to that of conventional concrete pavement. Now what we need to understand here is, in the case of a conventional concrete pavement, the foundation is basically represented by a set of springs. And these springs, the parameter what we represent for the spring is modulus of subgrade reaction K. Okay. Now, what is happening in the case of white topping? In the case of white topping, I'm keeping a concrete slab above a bituminous surface. So the K value, the foundation basically becomes the old distress pavement, which is basically leveled. So we need to consider the K value of the foundation correctly. So there are charts which are actually provided in IRC SP 76 to determine the effective K value. So let me repeat again. In the case of conventional concrete pavements, we analyze the concrete pavements by considering that the slab is resting above a Winkler foundation. So basically all your subbase layers, your subgrade layer, the strength of your subbase layers and your subgrade is represented by what is referred as modulus of subgrade reaction K. Now coming to white topping, your slab is resting above a bituminous surface. So basically the foundation, it comprises of the lower subgrade, consists of our granular layers, and also it consists of a bituminous surfacing. So basically we need to find out the effective K value. So for finding out the effective K value, there are charts which are provided. So you can find this design chart. We need to know what is the K of the subgrade. Basically from soil CBR, we can estimate the K of the subgrade. We should know what are the thicknesses of the granular base layers. So there are different charts which are actually provided for different granular thicknesses. So we need to identify, say from our subgrade CBR, we can identify what is the K value from the table which is given in IRC SP 58. From there, you identify your granular layer thickness. You should also be aware of your thickness of your bituminous layer. So if you know the thickness of your bituminous layer, you initially you travel horizontally. You arrive at the line corresponding to your granular layer thickness. Once you identify your granular layer thickness, project to the top to the line where we have our thicknesses of our bituminous layer. From there, you again travel horizontally to the right, identify the effective K value of your foundation in the case of white topping. So this is the procedure for determination of effective K value over existing bituminous pavement on the top of the granular subbase. Now there are design charts in IRC SP 76 2015. There are design charts which are actually proposed for slabs having thicknesses between 100 to 200 mm. So the most critical stress combination which is considered in this guideline is corner load stresses and curling stresses. So similar to our conventional flexible payment design guideline, basically we are concerned about wheel load stresses and our temperature stresses. So wheel load stresses, since it is a panel concrete pavement, the most critical wheel load stresses would be the scenario when the load is at the corner. So corner load stresses plus curling stresses shall be less than the flexural strength of the concrete used. So this is the design philosophy. So if our traffic volumes are higher, the fatigue criteria which is given by IRC 58 2015 shall be considered. So there are design charts. There are design charts which are actually proposed for different panel sizes. For different panel sizes, okay. So you can choose the particular chart based on the panel size you are initially selecting for the trial panel size. For whatever panel size you have chosen, identify the corresponding design chart, and you can actually vary your trial thickness. So the combined flexural stresses by the load as well as the temperature stresses are given. So you can actually identify, corresponding to a thickness of say 150 mm, you can identify what is the flexural stresses that is occurring in the slab. So you need to compare this value to the flexural strength. Similarly, you can there are also design charts which are provided for different joint spacings also. So you can see as the joint spacing increases, our flexural stresses increases. So the idea is go for smaller panel size. When you go for smaller panel size, your wheel load induced stresses as well as your curling stresses are reduced. Now, when it actually comes to low volume roads, a more appropriate paper or a more appropriate research was basically carried out by Arun Chand and Professor B.B. Pandey from IIT Kharagpur. So this paper was published in the Indian Road Congress journal in 2013. I would actually share this paper. So you can see the paper number is 605. I would be sharing this paper with you. So there are design charts. There are design charts which are actually proposed for different panel sizes. So you can see the panel sizes, what they have considered is from 0.5 meters into 0.5 meters to 2 into 2 meter panel sizes. And the foundations, whatever they have considered is, they have considered granular foundations, treated foundations, cement treated foundations, and with lean concrete bases. Now let us understand this. Because this would be very useful whenever we are going for new constructions. So let us understand what all parameters we should know. When we are designing a short panel concrete pavement. So again here the analysis was done considering the concrete pavement resting above Winkler foundation. Now when it is resting above Winkler foundation, we need to know these K values, the spring constant values. To get the spring constant values, our IRC 58 for conventional concrete pavement, based on the CBR value, it has actually given what K values we can consider. So this is the scenario if the slab is directly placed above a compacted subgrade. We generally don't encounter this, but this is a scenario when the slab is directly placed above the compacted subgrade. The second scenario is when the slab is actually kept above granular subbase layers, having thicknesses ranging between 150 to 250 mm, subgrade having a certain strength. Okay, subgrades having a certain strength and granular layers of this particular thickness. These are the range of K values what we can consider. Similarly, for cementitious subbase layers, suppose if I am providing cementitious subbase layers having thicknesses between 150 to 200 mm, these are the K values what we can consider. So what we need to understand is, what we need to initially do is determine our K values. Now, once we determine our K values, these design charts proposed in this paper was given considering the flexural stresses along the edge. Basically, these panels are very small. These panels are having the size of 0.5 meters into 0.5 meters, and the highest panels is what they consider as 2 into 2 meter panel. So this is the loading consideration what they have taken. A dual wheel set, basically with a tire pressure of 0.8 MPa, with a tire pressure of 0.8 MPa, a wheel load having 50 kilonewton. This was the a wheel load having a dual wheel load having 50 kilonewton was being considered. So the analysis was carried out using ANSYS final element package. Now let us also understand what are the other assumptions what they considered. From one panel to another panel, they considered that there is no load transfer across the joints to the neighboring panels. Although in actual scenario, even though we cut a groove to 1/3 depth, there will be load transfer to the neighboring joint. So basically, they have considered the worst scenario. They have considered that there is no load transfer, so this is more conservative. Now, another thing what they considered is the interface between the slab and the subbase is considered as a smooth interface. So this is because in most cases, say for example, even in the construction of a cemented subbase and a concrete slab, your concrete slab will be constructed maybe after some days after your cementitious subbase construction. So you don't tend to get a good bonding between the slab and the subbase. So basically here, the interface between the slab and subbase is considered smooth, or you are not considering bonding in this analysis. So these are the design charts. So how one can choose is we need to consider a certain panel size. We can either go for 0.5 into 0.5 or 1 meter into 1 meter panel size. Okay, so once we have actually selected our panel dimensions, so I think this is basically for slabs of thickness, 75 mm. Okay, so once we have chosen a particular panel dimension, there are design charts which are proposed in this paper, from which we can identify our flexural stresses. So here, these 3 lines basically corresponds to three foundation conditions. 3 foundation conditions represented by K value. Okay, so you can come and identify what is the flexural stresses. We can come and identify the flexural stresses. So the only thing is your flexural stresses, whatever you are getting for a particular panel size, should be less than your flexural strength. So you can find that once you review these design charts, you can find that the flexural stresses reduces drastically by more than 60% when the panel size is reduced from 1.25 mm to 0.5 mm. So you can see for smaller panels, the load-induced flexural stresses are much less. So that is a significant reduction of flexural stresses. Now, as the selected panel size increases, so when we increase the thicknesses, of the concrete slab, our flexural stresses also tend to decrease. So one need to optimize the thickness and your slab dimension. So thereby you can even have concrete pavements having a thicknesses less than 150 mm. So in this paper, it is actually concluded that a 75 mm thick concrete slab with a panel size of 0.5 meters into 0.5 meters will develop only 2.6 megapascal flexural stress under a dual wheel load of 50 kilonewtons and can be a cost-effective solution for village roads. Now, panel concrete will have a long-term performance provided this is constructed above a non-erodable subbase, such as a dryling concrete or a stabilized or a stabilized subbase layer. Now these are the design charts. So I have actually put up the design charts for different thicknesses. So this is the design chart for 50 mm thick slab, for 100 mm, for 75 mm, for 100 mm, and for 150 mm. So what you can identify is, as the slab dimensions, as the slab thicknesses increases, you can find, say suppose I take corresponding to 1 meter slab dimension. This is my flexural stress I'm getting. Say if it was at 50 mm, say this is the magnitude of flexural stress. So as the slab dimension increases, my flexural stress is actually reducing from 8 megapascals to 3 megapascals. And from this graph, we can also understand that as my panel size is reduced, my flexural stress is also reduced. So if one has to go for short panel concrete pavement, we need to optimize between your slab dimension, your panel size, and your thickness. Okay, so this was one of the short panel concrete pavement executed by engineer Rajiv Chattaraj sir in West Bengal in Burdwan district. So you can actually find this as a stone pitch pavement, which was in a very bad condition. It was actually having surface irregularities. There were surface deformations there. So what they did was they actually placed a leveling course of wet mix macadam, On the top, they actually had lean concrete. They placed a dry lean concrete of M10 concrete grade. On the top, they placed an M40 grade concrete M40 grade concrete having a thickness of 150 mm, and they did not reduce the thickness. They for a conservative side, they kept a thickness of 150, even though 150 thickness was not required. They kept on a conservative side, they kept a thickness of 150 mm. So you can see the construction photographs. Now the main thing in the case of short panel concrete pavements is that you have to mobilize sufficient cutting equipments. So within 8 to 9 hours of construction of your PQC, these panels have to be these panel grooves have to be formed. Now, if you are unable to mobilize these many number of cutting machines, you can even keep plastic sheets. And then divide your panel dimensions. Now, if you're using a cutting equipment, the depth of cutting shall be up to 1/3 depth. Now, okay, so for cutting grooves, for such a small scale work, diamond cutters fitted in handhold small machines were used. So once cutting was done, this was actually subjected to curing. So soon after grooving, it was subjected to water curing, and it was maintained for 28 days. This is one photograph where you can actually find Professor B.B. Pandey, who initially proposed the concept of short panel concrete pavements for low volume roads in India. So the stretch of short panel concrete pavement carried the usual traffic of that of a state highway with a commercial vehicles per day not less than 750, and it is still in a good condition. But in some locations, there are some cracks that is observed. Now let us actually come to the second type of pavement which we will be discussing today. That is what is referred as self-fill concrete pavements. Now I told this is also coming in the category where we are trying to reduce our slab dimension. But here our slab dimensions are reduced to such a level that the load transfer in the case of self-fill concrete pavement is not happening like a conventional concrete slab. In the case of a conventional concrete slab, we have slab action coming there. But here, in the case of self-fill concrete pavement, you find concrete being filled in these plastic cells. So you can find a honeycomb shaped structure. These are basically plastic cells. This is basically a grid of plastic cell. Okay. Now this grid is made by welding these joints. These are made by heat welding, or these are either stitched also. So in this in these honeycomb shape structure, concrete is being placed, and it is being compacted. So depending upon the workability of concrete, you have to adopt an appropriate compaction equipment. So once concrete is poured into each of these cells, so we have concrete, we have concrete, and between two blocks, we have a plastic sheet, which is basically a flexible separation. So the load transfer here is not based on slab action. So you have interlocking. So this can be considered as a cast in situ. This can be considered as a cast in situ interlocking block pavement. Okay, if you remember your block pavements, you have we have block pavements which are precast block pavements. We tend to arrange it in the, or we tend to construct this in the field. But whereas in this case, in the case of self-fill concrete pavements, these are cast in situ block pavements. Okay, so this has very short spacings with a unique arrangement, thinner concrete layer with multiple joints, and hence the load is spread not by slab action. Basically, once you place concrete, and once you start compacting, the plastic sheets will tend to bend. So when the plastic sheets tend to bend, they tend to give interlocking from one cell to another cell. So basically there is interlocking between one cell to another. This is how load is transferred from one cell to another cell. Yes, I have a schematic diagram here. So once you pour concrete, and once you start compacting this, the plastic cells tend to bend at these interfaces. Once the plastic cells tend to bend at these interfaces, and once the concrete hardens, you have interlocking which is mobilized between these two. Okay, so that is what I have written here. As plastic cells are filled with concrete, it forms a flexible layer having a rigid material. Now, the typical thicknesses, the typical depth of this concrete layer can be between 50 to 100 mm. We will talk about how do we design this in the subsequent slides. Okay, so try to understand. This is we are not using a concrete pavement design philosophy for designing self-fill concrete pavement. We use a different design philosophy for designing this. Now, the flexible rigid layer should be basically there is a you have a flexible interface between two concrete surface. So the flexible rigid layer should be subjected to limited rotation at the joints. Say otherwise, what happens is these cells will tend to get separated away. Say for example, whenever we are preparing a self-fill concrete pavement, towards the edge side, if we don't provide constraint with respect to time, you will have these cells getting disintegrated with respect to time. Now, since slab dimensions are brought very small, you have negligible temperature stresses here. Now, interlocking between the blocks is very crucial for performance. This has to be placed above a non-erodible compacted foundation. Now, as I told you, the design philosophy in the case of self-fill concrete pavements is not like a conventional concrete pavement. Here, this is each individual cells. Basically, these are each individual concrete blocks are there. So this will actually act as a flexible layer. So the design of self-fill concrete pavements is basically done by our flexible pavement design philosophy. So here, as the dimensions is very small, as the thickness of the slab is very small, we will not be getting flexible stresses in the slab. As a result, cracking is not considered while we design self-fill concrete pavement. We tend to use the rutting criteria for design. So the 80% reliability criteria is used. The 80% reliability criteria, which is provided in IRC 37, which is provided in IRC 37, is actually used for the design of self-fill concrete pavements. So this is the Rutting equation, where epsilon z is the vertical compressive strain which is coming onto the top of subgrade. So there is a PMGSY do-it-yourself manual. There is a do-it-yourself manual which is given by NRIDA. So in that you can actually find the thickness requirement, the total thickness requirement of all the layers, including the slab. So basically this is the total thickness, including the granular layers. There are design charts which are proposed. This will actually facilitate a pavement designer based on his traffic levels, and based on the CBR condition, you can determine what is the total thickness of the pavement required. And if you want to do the pavement analysis using IIT Pave, you have to provide a moduli to this particular layer, and the moduli which is suggested in this particular manual is 2000 megapascals. Now, coming to the construction part of this, you can use conventional concrete, or you can go for zero slump concrete with a characteristic compressive strength of 30 MPa. You can even go for higher strength concrete also. Even for 40 MPa you can go, M40 concrete you can go. Now, in the case of zero slump, practicing engineers place zero slump concrete. Now, in that scenario, you can start filling. The cells. Basically, you need to stretch this plastic cells. And we tend to anchor the cells using steel bolts. Once you anchor this, you start filling the cells from one corner. So, if you use zero slump concrete, once these cells are filled with concrete, you can use a conventional static roller of 6 to 8 ton capacity for compaction. Now, if you're using a normal concrete, a slump value, having a slump value of 50 mm, you will have to use what is referred as plate vibrator. In this scenario, your length of work that you can complete in a day will be typically low, unless you tend to mobilize more number of plate vibrators. Now, during compaction, basically these cells tend to bend. These cells tend to bend. So once these cells tend to deform, and once the concrete sets, they tend to start developing interlocking. Now, these plastic cells, they're typically HDP or LDP, high density polyethylene or low density polyethylene, having this particular thicknesses. So the joints between these cells are basically hot welded, or it also comes in a stitch way. So there are manufacturers available in Bangalore, in Kolkata, and all. There are manufacturers available which tend to provide these self-fill concrete plastic sheets. So you can get these strips. According to your thicknesses, and as well as to the width and length as per your requirement. You can get these. You can get these plastic sheets in the form of rolls. Okay. Now this is how you construct this. You need to stretch the plastic sheet. The main advantage is basically, when compared to your conventional concrete, your thicknesses is much less. So you can have thicknesses of the order of 80 mm, 100 mm, like that. Okay. So you initially you would stretch this. you would anchor this by means of nails, okay. And once you fill the end cells, you can start pouring concrete from the edge, and provided you actually go for a zero stump concrete pavement, your construction would be relatively faster when compared to conventional concrete. Now there are three approaches. So before going for any of these three approaches, we have to ensure that there is edge restraint. We have sufficient edge restraint. So there are three approaches. In the first approach, this is the first approach, where we tend to fill the cells, with a single size aggregation. Okay, we tend to fill the cells with a single size aggregation, and we pour cement grout. Of sufficient consistency or sufficient flow value. So when you're actually providing cement grout of sufficient consistency, the cement grout, when you tend to provide some amount of vibration, the grout will tend to penetrate inside, and thereby you could complete the construction. So this is the first way of constructing this. Fill the cells with single size concrete, with single size aggregates, lightly compacted with road roller, so that or you can go for a vibration also, so that you tend to mobilize good interlocking. Further, cement grout of sufficient flow value is grouted. Now in the second one, where you can go for a conventional concrete, but you will have to use a pan or a skid vibrator. So this would actually take you more time. The third approach is you can actually go for a low slump concrete. And you can use your conventional road rollers to compact these filled layers. Okay, so these are the photographs of the first self-fill pavement. Basically, this is a patented technology of Professor B.B. Pandey from IIT Kharagpur. Now, this is the first low-volume road which was constructed near Kharagpur in West Bengal. So you can see the plastic being stretched, and you can see nails being applied, and the construction starts from the edge, from the corner. And once suppose you are using a low stump concrete, once you fill this, you will get a working platform. Thereby, you can proceed your concreting towards inside. Now you can see the cells being or the concrete being compacted by means of vibrators. Now, say after compaction, you may actually get an exposed surface of plastic, but that will not cause any problem in your pavement performance. Although aesthetically, you may actually find these cells very clear. Maybe after 2 months, 3 months, you may have some amount of polishing, so you may tend to see this cells very clearly. Okay, now these were the construction photographs. Now once you tend to complete your concreting and your compaction process, you can apply curing. Curing can be applied by either moist curing. These are moist paddy straws, or you can even go for water ponding. Okay. Now, opening to traffic. When it comes to opening to traffic, you can open this to light traffic after 2 days. But whereas iron drum bullock carts and heavy traffic such as buses, tractors, etc., can be permitted only after 14 days. Now, regarding the lower layers, we need to provide a minimum of 100 mm of GSB is recommended. And for higher design traffic, we can actually go for cementitious surveys. Basically, this is similar to your interlocking block pavements, where the success of any of these block pavements is basically how well you compact your lower layers. Your lower layers should be sufficiently adequately compacted. Now, this is one of the trial stretch, one of the study stretches what we have carried out in Kerala by NIT Warangal and St. Kitts College of Engineering, Kottayam, where we have constructed 4 sections. Basically, the Kerala state government, it actually funded for 16 test sections, one after the other, in a low volume road. Each of these stretches were having a length of nearly 40 to 50 meters length. So we had 4 sections with concrete, and we have remaining 12 sections with flexible payment combinations. So I'll be discussing only the 4 combinations of concrete. So it is a usual practice in low volume road construction in Kerala, in the state of Kerala, to go for a concrete slab of 10 centimeter thickness. I'm not talking regarding construction in the case of PMGSY roads. I'm talking about rural roads which are coming under the local self-government department in Kerala. So they had a practice of going for 10 centimeter concrete slab placed above compacted subbase layers or compacted granular layers. So this was the conventional stretch, and the second stretch was basically a short panel concrete pavement. So what we had was, we actually had sections one after the other. So this is conventional concrete, and we had a short panel concrete. We actually had interlocking block pavement, and we had self-fill concrete pavements. Okay, so this was the conventional one. This was a short panel concrete pavement. This was a short panel concrete pavement. You can see the panels what we made was having a dimension of 0.5 meters into 0.5 meters. And this is the test section with interlocking block pavements. So you can see the edge restraint here. But although this is not the right practice, you should actually have your edge restraint initially before construction. Now, this was the construction of interlocking block pavements. Here we actually went for conventional concrete. Although we would have rightly went for zero slump concrete, we adopted conventional concrete layer. So these were the 4 test sections: conventional concrete, self-fill concrete pavement, interlocking block, and short panel concrete pavement. Now, quality control studies were carried out. Concrete was collected while paving activity was in progress. Cubes, beam specimens were casted for different quality control tests. Now, one of the major testing what we carried out was the deflection studies on these concrete pavements. We carried out deflection studies using falling wave deflectometer, which was available with KIFB. So this is basically the falling wave deflectometer, where you can find the loading plate and the geophones. So the experiment basically consists of dropping a load here. So once a load is dropped, the pavement will actually tend to take a deflected shape. Okay, so for 4 of these pavement section, your conventional concrete of 100 mm dimension, of 100 mm thickness, was having the lowest lowest deflection, indicating that is a structurally good pavement, followed by our short panel concrete pavement, followed by self-fill, and followed by our paving blocks. But I have not plotted one more graph. When compared to a conventional flexible pavement surface with premix carpet surface, all of these 4 concrete sections, even after 2 years of construction, even after 1 year of construction, was exhibiting an improved structural strength when compared to the conventional flexible pavement. So the way forward, we need to adopt or we need to go for long-lasting payment technologies which are cost-effective also. So as you all understand, our concrete payments, it has a bright future, but our major problem what we encounter is the higher initial cost of construction. So you can consider any of these relevant technologies what we discussed today in the class, such as going for short panel concrete payments, where you can reduce your payment thicknesses of the order of you can reduce it by something like 100 mm or even 75 mm by choosing an appropriate panel size. That is the first option. The second option is you can actually go for self-fill concrete payments also. In my subsequent class, I would be also discussing about what is referred as we would be discussing about roller compacted concrete payments, and as well as interlocking block payments. Those are also two new technologies that you can adopt. So thank you. If you have any queries, I'm ready to answer.